Welcome everyone to the CSE 234 Industry Guest Lecture. This is Data Systems for ML. My name is Arun Kumar. It's a pleasure to introduce Dr. Sudip Roy. And Sudip is at Cohere, one of the hottest startups in the NLP space, NLP as a service space. They're working on LLMs, which, as you all know, has been all the rage around the world in the last half a year, at least, if not a couple of years. Sudip I've known him for several years from the database systems world, met him at a SIGMOD, I believe, where he actually won a Best Paper Award. And Sudip is now manager of technical staff at Cohere, where he's working on this NLP technology, but he's also, like me, straddled database systems for ML, and he's published at MLSys, the new ML Systems Conference, and he's won an award there as well. But he also does ML for systems, especially compilers and OS kind of stuff. And he's now at Cohere responsible for serving state-of-the-art LLMs that power Cohere's APIs and products. And he's going to share with us some of his thoughts on the history of ML systems and open challenges, including for training and serving LLMs. So just a protocol for the talk. Audience, feel free to raise your hand and ask questions. Sudip is okay with taking questions during. If you have longer questions, I would suggest waiting till the end if there's a lot of back and forth so that we can progress with the talk. Feel free to also post questions on the chat. I will monitor that as well. With that, the floor is yours, Sudip.
Great. So I'm going to start with a disclaimer. If you happen to watch my talk a couple of weeks ago for C4AI, then this is going to be a very similar talk. So I'm going to save you some time. So I won't mind if you drop out if you have already watched the talk. But yeah, thank you for the introduction, Arun. It's a real pleasure to actually have the opportunity to interact with the students and give this talk. I'm going to start by just summarizing my research journey, which I think to some extent Arun already summarized. As Arun mentioned, I started as a researcher in data management, and over the years, I have increasingly moved more and more towards machine learning. In the space of machine learning itself, I worked on many aspects, including end-to-end orchestration for ML, did more work on core systems, especially in developing the next generation of machine learning infrastructure for training and serving large models at Google, as well as worked on applying ML models to solve complex optimization problems in systems and ML compilers. At Cohere, I right now lead the inference team, which is responsible for serving all of the large language models. And throughout this journey, as I have shown on the slide, I've published in a number of different conferences. And in general, I'm interested in working on interesting problems instead of limiting myself to a single domain. But as a consequence, I'm also likely not a top expert in a very narrow domain, but more of a generalist researcher, which almost sounds like an oxymoron, right? Finally, I wanted to put again another disclaimer that the opinions that I express in this talk are my personal opinions and not necessarily the opinions of my current or previous employer. With that, I wanted to just take one slide to talk about what Cohere does. As Arun mentioned, Cohere is actually one of the startups which is trying to make NLP universally accessible to all developers to do interesting stuff with. And as part of this, we provide an API for developers to build on top of the large language models that sit behind them in order to bridge the gap between the requirements that a customer or a user would have and what the large language models actually provides. We have these what we call as endpoints, which are basically some business logic that sit on top of our large language models that basically enable it to target very specific verticals. So for instance, we will have an endpoint for summarization, another one for content moderation, for classification, and so on and so forth. So that will pretty much be my only slide that is very Cohere specific. I think the rest of the talk is going to be very general and talk about, in general, what I see in the space of ML systems. So I'm going to cover this talk in 3 parts. First, I'm going to present like a brief recent history of distributed ML systems. And as part of this historical view, I'll also discuss some of the trends that I currently see and how that might inform the systems that we need to design in the future. And in the second part, I will identify a few semi-concrete open technical challenges, which are more related to training. I will also briefly present an overview of a system that addresses some of these challenges. And then in the third part, I will identify a few, again, semi-concrete open technical challenges related to serving. And these will be mostly rooted based on our experience in serving large language models at Cohere so far. Yeah, as Arun mentioned, feel free to interrupt me at any point in time as you have questions. So let's start with like the first wave of ML frameworks. And this was, I guess, maybe around a decade ago, right? This was an era where the hardware used for machine learning and deep learning was relatively simple. In many cases, you would just use CPUs for training and inference. And if you did use accelerators, there were mostly either 1 or 2 accelerators connected to a host. And these machines were connected to each other over the relatively slower data center network links. And on the ML side, it was this kind of hardware was actually perfectly fine. The models were relatively small with at most hundreds of millions of parameters. And consequently, the computation requirement was also small. So these models would easily fit onto a single accelerator, and you would rarely need to actually talk to another set of accelerators over the slow data center network. And the frameworks for this era basically adopted a single controller model. And the single controller model was largely inspired by prior non-ML frameworks like Dryad and Spark. And in the single controller model for distributed execution, you have the user code running in one process, delegating computation to a collection of workers via a distributed system. So you have the client, which is running a Python code. It basically constructs a graph that is shipped to the controller. The controller is then responsible for executing this graph that defines the user's computation over potentially a bunch of different workers. But as I mentioned, the models themselves were relatively simple. So in many cases, you would just have like very few workers, if at all. So there was it was like very simple computation systems to that extent. As a consequence, though, that any coordination between the workers in the form of data and control edges would require this communication over a relatively slow data center network. Because the controller was sitting in another place, you have workers sitting in another place, and they would continue. They would need to communicate frequently over this slow link. And the biggest benefit of the single controller system, and this was what was adopted in systems like TensorFlow V1, is that it's a very general distributed data flow model. And it could support things like optimized in-graph control flow. The other advantage was that it was possible to do virtualization of hardware resources. For instance, because you had the single controller and your workers were somewhat abstracted away from the user's computation, the controller could actually be used by multiple different clients, and these clients could share the shared set of workers. And any scheduling would then be done by the controller itself. Now, none of these systems actually implemented it, but at least the design permitted the use of these multi-tenancy and virtualization. But there were 2 fundamental problems that the single controller design had. The first is just scalability. As you have increasingly larger number of accelerators, the amount of work that the controller would have to do would also correspondingly increase. And at some point, it would just become a bottleneck. And it wasn't much of a concern, again, for the first wave where the models were relatively small. You had only a few number of workers, so it was never the case that the controller had actually become a bottleneck. And the second was latency. As I mentioned, in the single controller setup, you would have this controller, which is basically sitting at least one data center network hop away from the host machines that for the accelerators. So you would always be communicating over this relatively slow network. So in order to overcome some of these challenges, there was innovation that happened both in hardware and software space to keep up with the requirements of machine learning. In the space of hardware, it was increasingly possible to have a large number of accelerators connected to each other over high bandwidth networks. In the case of GPUs, it was NVLinks. In the case of TPUs, it was ICIs. And this basically meant that the accelerators could talk to each other without necessarily even talking to the hosts themselves, right? So you do not have to, you could eliminate not only like the data center network connection, but you could also eliminate the PCIe connection of talking to the host itself. And on the machine learning side, it was increasingly apparent that the larger models not only tend to produce better quality results in many cases, but also there are certain emergent abilities of these models that only manifest at certain scales. This was also an era where researchers realized that it is possible to develop some foundation models that can be trained with abundant unsupervised data. And these foundation models can be really good at a number of different tasks. And what this shift meant was that it justified the development of really large and expensive models, which are trained on massive amounts of compute for long periods of time, because you could actually train this one model that could actually solve a bunch of these tasks. So it made sense to spend a lot of money in trying to build this model. And on the systems and frameworks side, what this meant was distributed systems mostly adopted a multi-controller architecture. And in this multi-controller architecture, you have the exact same client executable that is run directly on the host machines. And that takes exclusive ownership of the hardware resources. So there's no sharing of the hardware resources between other client computations. And this is what you usually refer to as SPMD pattern, right? So single program, multiple data. So you're sharding the data across the computations, but you're basically running the same copy of the program on each of your machines. And examples of this architecture include things like MPI, or in more modern context, I guess, JAX, as well as PyTorch and some more recent configurations of TensorFlow. And the key advantage of this architecture is basically that the low latency of dispatching accelerator computations, since an identical copy of the user's code runs on each of the accelerator hosts, and the dispatch only requires a fast communication between, only requires a communication over a relatively fast link between the host and the accelerator, as opposed to in the single controller case, where the controller was sitting one data center network hop away. Right now, the computation is just dispatched from the host itself. There is no single controller. And after this dispatch, all of the other communication across the hosts only happens through collectives that use these dedicated interconnects, like NVLink. So the hosts themselves never need to talk to each other because they're exactly the same program. Any communication that needs to happen across hosts happens through these collectives, which use the high bandwidth interconnects. So this actually, I guess, style of computation worked really well for a long period of time, right? And in fact, most of the models that you see today are still using this SPMD paradigm. However, this is somewhat limiting because you are stuck in a regime where you basically have to respect this SPMD programming style, and any deviation from it is really non-trivial to implement. The other key disadvantage of this is that it assumes that you have exclusive ownership of hardware resources. Because your computation is running on the host machines and the hosts never talk to each other, you basically need to assume that there's no concept of a shared worker pool. You are the user who is running the computation exclusively owns the hardware for the entire duration of the computation, so that you cannot have any virtualization or sharing of the hardware across multiple users. And that's fine from the user's point of view, but it makes it really cost inefficient. And from the cloud, let's say cloud service provider's point of view, it doesn't allow cost optimization, which is, again, like one of the big problems. So with that background, let's now talk about some of the trends to understand why these existing frameworks are incapable of supporting the computation patterns that we expect to see in the future. And I'll identify these trends in a number of different segments. In the space of hardwares, due to the rapid innovation in the space, most cloud service providers now have heterogeneous collection of accelerators. They are both different generations of the same hardware, as well as different types of accelerators. For instance, you would have GPUs and TPUs, different generations of GPUs, different generations of TPUs, and so on. And this diversity is only likely to increase in the future, right? There's like all new types of hardware, like wafer scale chips and others that are being brought on the market. Yeah, naturally, this diversity is just going to continue to increase. So it's natural to expect that our systems and computations need to be flexible enough to be able to leverage this diversity so that we can ensure high cluster utilization. Second trend that I see is just the scale. OpenAI released this interesting analysis a few years back showing that since 2012, the amount of compute used in the largest AI training runs has been increasing exponentially with a 3.4 months doubling time, as opposed to, let's say, in the pre-2012 era, where it was following more or less Moore's law. Yes, I think someone had a question.
Hi, my name is Mayank.
Hi.
On the previous slide, you were talking about the accelerators and how you're using, many companies are using heterogeneous accelerators. So how do TPUs are significantly faster than GPUs. So how do you go about designing which computation goes to which machine?
So I don't think TPUs are significantly faster than GPUs. They just have, it really depends on which generation of TPUs we are talking about and which generation of GPUs we are comparing them to. For instance, like the peak flops of the A100 or H100s are higher than the peak flops that you would get from a V4 TPU. But having said that, I don't think people today actually run computations in a hardware agnostic way. So when you run your machine learning model, you are explicitly defining your computation for a specific type of hardware. So I'm talking about a future in which we should be able to actually leverage different types of hardware, but we're not quite there yet.
Okay, got it. Thank you.
Great. So as I mentioned, like OpenAI basically released this analysis, which basically showed that now we are kind of in a phase where the AI compute almost doubles every 3 or 4 months. And this is likely going to continue over the next few years. And clearly, I don't think if we just look at the hardware innovations, they are going to keep up with this doubling of compute requirements. And one of the reasons why this is likely to continue is papers like this, which basically say that there are certain emergent abilities of these large models that manifest at certain scales. So if you are which basically means that we'll continue to push increasingly larger and larger models. Now, there's also, to be fair, there's also research which basically shows that these large models are massively undertrained, and you are much better off training a smaller model for longer periods over larger volumes of data. So these two trends are, I guess, to some extent conflicting, but I still see that we would both be training smaller models over larger data sets, as well as training larger models just to uncover this emergent abilities. And the third is we are increasingly likely to deviate from the standard SPMD computation pattern. In fact, it's fairly common these days to use pipeline parallelism in addition to data and model parallelism, where you split the model into stages that are assigned to different sets of devices. There's also a new dimension called sequence parallelism, which just makes this problem even more complicated. And the system, the frameworks that you have today do not necessarily support this deviation from traditional SPMD computation pattern easily. As I mentioned, like the second generation really requires you to follow this SPMD paradigm. The second trend that I see is increasingly, we basically want to invest in sparse models. And what you can imagine is that a typical deep learning model would activate each of the neurons that are part of the model for every example, right? In order to do an inference, it's not like you're actually choosing a subset of parameters. It's just a dense model, so it's going to activate the full network. But if you consider the human brain, that's not how a human brain would work. We only activate certain parts of our brain in order to do a particular task. So there's this type of models, which is called like the mixture of experts, which are basically, which have a gating network within a gating function within the network itself, which basically decides which parts of the network to activate based on a particular example. And that's all fine, but for these kinds of innovative, non-dense patterns, the frameworks do not necessarily have good support, because what you're effectively doing with this gating function is you have a conditional computation, at which point you cannot stick to the SPMD paradigm anymore. You need to deviate from that. And then one of the most powerful ideas in deep learning is that sometimes you can take the knowledge learned from one task and apply that knowledge to help another task. And this has been true to some extent, given the development of foundation model that are basically a base set of models that are good at a wide variety of tasks. Even so, if you really want to eke out like the last bit of performance for a specific task, you're likely to fine tune them for different tasks. But still, we do want this. There is a trend to actually train these foundation models, but also have them train over multiple tasks. So, so that they can learn shared representations of concepts and not just expressed across multiple tasks, but also expressed through multiple modalities, including vision, text, audio, potentially perception in the future, and so on. And finally, increasingly, we are likely to see deeper integration of machine learning models with other standard standard existing systems that we are very familiar with, whether it's search engines, databases, or knowledge graphs. And this, so right now, with this I guess, competition is fairly in its infancy, but increasingly we are likely to see much more deeper integration between these two types of systems. And the last trend that I anticipate seeing is basically an increasing focus on cost efficiency. So you can take it with a grain of salt, but most technologies follow this innovation S-curve, in which in the early days, you need to spend a massive amount of time and resources to get marginal improvements. This is usually like the research and development phase, in which you want to get the technology to a point where it is actually useful. And then there's the second phase where there's a steep growth and rapid innovation where the technology is actually converted to a product. And finally, there's this maintenance phase where the technology largely saturates and has been commoditized. And I believe when you see what's happening in the field of large language models, we're basically at the cusp of this first inflection point where in the past few years, we have devoted massive amounts of time and resources to get these language models to a point where they are actually, they can actually deliver quality, which is easy to productize. And as a consequence of that, what I am going to increasingly, what I increasingly expect to see is a focus on cost efficiency as you actually try to integrate this product, integrate the technology into products and sell it, because there is going to be an arms race. And if you're following the news, then technology like ChatGPT, it can be really expensive to serve when you have a large number of users. So just to summarize these trends, we basically, as I mentioned, instead of the hardware that we saw in the second wave, which was basically a single type of hardware connected over high bandwidth interconnects, we are going to see large islands of heterogeneous types of compute. In the space of machine learning, we are going to see researchers increasingly wanting to try a diverse set of computation patterns that do not necessarily fit SPMD. And we are likely to see a continued focus on both scaling to larger and larger models, as well as a focus on cost efficiency. So a natural question to answer is, what sort of systems and frameworks do we need to develop in order to tackle these new trends? Because clearly, like the first and the second generation frameworks that we currently have cannot address many of these trends that I just showed you. Any questions at this point?
I have a question, Sudip.
Yeah.
I want to know what challenges the multimodal nature of data presents, because like the way I look at it is to the model itself, the data type is sort of abstracted away, right? Multimodal data is just represented as vectors or matrices. So how does the fact that the data is coming from different modalities actually impact how you think about the frameworks?
So that's a good question. I guess in order to integrate these multiple modalities, you need to first do a projection of whatever the formats these modalities are presented in into a somewhat shared representation space, right? So you would have these base set of layers, which are different for each of these modalities. And then you project, and then you have a shared trunk of the network. And then you potentially have multiple heads on top for solving different types of tasks. You can imagine that there are multiple types of challenges that you need to solve in that case, right? One is just on the data side of things. How can you actually handle the data processing, which can actually be very substantially different across each of these different modalities? How do you deal with missing data in the sense that you're not going to necessarily have all of these modalities specified for each of your examples? And then, so yeah, I guess these are like a couple of examples of how I see multimodal to present its own set of challenges. Yeah, hopefully that like answers part of the question.
So primarily like it would impact the data processing part of the pipeline. And then once I guess that's done, then you could think of the ML framework, like in a more broader sense. Is that right?
So yes, well, partly data processing, but as I mentioned, like the base set of network layers are going to be different for each of your modalities. So the ML framework itself needs to be able to efficiently run this computation, which again might deviate from the standard SPMD pattern, because each of your different modalities is going through a slightly different computation path in your network.
Got it. Thank you.
So Sudip, I also have a quick question building on that. One of the things that system designers look for is, what are the access patterns that you expect? What are the communication patterns, for example? Do you anticipate attention models withstanding the test of time? And do you think the communication patterns and stuff you'll see will be sequential feed-forward models with giant matrix multiplications? Or do you see with sparsity and stuff like this, random kind of graph-oriented access patterns that might lead to ad hoc communication across devices and stuff?
So let me come back to that in a couple of slides.
Okay, sounds good. Let's continue then.
All right, so I'm going to switch over to like the second part of my talk, which is going to be mostly focused around training. And then we'll have the third part, which is focused around serving. I want to be respectful of everyone's time, so but I want to answer any questions. So what I'm going to do is that I'm more than happy to just skip slides at the end, but let's keep things interactive and answer any questions. All right, so based on my experience of training these models, I think one of the key problems right now in training large models is basically reliability and fault tolerance, especially when you think of things at scale. Here, I'm just giving you a very rough example. Don't get too attached to these numbers. They may not necessarily make sense. And this is a very simplistic model. So let's assume that you have an individual accelerator chip, which has a mean time to failure of 5 years, right? Which basically means, which isn't all that bad if you look at it in isolation, right? If you have a GPU, you're likely to only use it for 5 years. Maybe in 5 years, you would actually, there will be like two or three new generations. So at that point, you definitely do not want GPUs to actually last longer than that. But if you look at a superpod of, let's say, 4096 of these accelerators, then if you assume this mean time to failure of 5 years, then you would actually expect a failure or 2.24 failures every day in your superpod of 4096 accelerators. And if you're running these SPMD type computations, they are going to stall every time any of these accelerators fail. And because your computation stalls, you might need some time to actually detect that the failure happened. You would probably have some checkpointing. You would have to reload your checkpoint. You may have lost certain steps that you took after the last checkpoint. So you are going to retrace those lost steps. And maybe this is actually a pessimistic example, but you might actually end up losing, let's say, 2 hours of your time for each of these failures, which means that you would lose maybe like 5 hours of your time per day. And as you can see, that amounts to like 20% of just wasted compute just because the hardware is inherently unreliable. And here I kind of shifted the full blame onto the hardware itself, but there's also other software processes that you need to do over such a pod, right? You may do a rolling rollout of software upgrades or driver updates, and each of those has the potential to actually cause a stall. So one of the challenges that I see is how do we make frameworks much more fault tolerant to these kinds of failures. And this is actually a fairly old paper, which is called Tail at Scale by Jeff and Louis. And they had written it in an era where we were talking about how to actually run data centers of CPU. And they're like CPU data centers. But as you can imagine, now we are kind of in a position where we have these thousands of accelerators which are packed into a single pod. So effectively, you are basically running almost like a data center, like you're running a computation on a full data center worth of compute. It's just that we don't have the fault tolerance mechanisms that we have at the level of a true data center built in to these frameworks yet. So that's one of the challenges that I think the community should work towards. The second one is how we express ML computations today. As I mentioned, most of the models require massive volumes of data and large amounts of compute. So efficiency in training is obviously like a requirement, right? And today, ML research is basically limited by what you can execute efficiently. So what ML researchers would often do is basically shoehorn the ideas to fit what you can do what you can execute efficiently. And one of these examples is, let's say, this sparse. I basically talked about this sparse mixture of experts type computation in which you are activating only certain parts of the network based on the example. And because this is not necessarily a SPMD computation inherently, because it has this conditional flow in the graph itself, what researchers have done is basically they have this way of making it, of basically like homogenizing it, in which they create batches such that, and have regularization so that all of the experts will actually get more or less a evenly sized batch, and all of the experts have the same number of parameters. So even though the computation is not truly SPMD, it very closely mimics SPMD, because that's what you can execute efficiently. So that's just an example of how researchers would like shoehorn ideas to fit what you can execute efficiently. But ideally, you would, as people in the data management community are very well aware of, you want computations to be specified in a declarative way, where you do not necessarily specify how to do the computation. You just want to say what computation to run, right? For instance, this is a paper which basically describes the transformer model and equations. Ideally, we should be in a position where we take these equations and, or what we basically paraphrase these equations in code, and then the frameworks take care of finding what the optimal execution strategy for the model is. But we are much far away from that, right? We need to today specify what the optimal parallelism based on the network topology is, how do we reshard tensors, and so on and so forth. So this kind of brings me to this interesting paper that Sarah wrote a few years ago called Hardware Lottery. And the key thesis of the paper is that a research idea wins because it is suited to the available software and hardware, and not because the idea is necessarily superior to the alternative research directions. And this kind of brings me back to Arun's question that a lot of, I believe, transformer type and attention models success is also based on the fact that it is really easy to execute that computation efficiently on hardware. And given that, the software ecosystem has also skewed very much towards that particular architecture. To the extent that you have libraries like Fast Transformer, which are very hyper optimized to serve specifically transformer type models. So whether there are other research ideas and other alternatives that are promising, I'm sure there are, right? There are things like capsule networks. And if you read this paper, it probably enumerates like a number of these other research directions, but some of them might just never see the light of day because we don't necessarily have the right hardware or software architectures to justify investing in those at this point. And that's just reality. A second problem that I basically see is the fact that because we are specifying not just not just what computation to run, but how we exactly run it, we are not in a position to transparently migrate the computation from one set of hardware to a different set of hardware. In an ideal world, a researcher basically specifies the model that they want to run in a declarative way. We have systems that support hardware virtualization. And if you combine these two, you basically get fungibility, so that your user doesn't necessarily say that this is the exact hardware and this is the configuration in which you need to run the computation. You basically just say, this is the computation that I want to run, and then leave it to the system to run it on one set of devices. If that set of devices becomes over-constrained, or for whatever other reason, one of the devices fails, the system has complete freedom to migrate it automatically to a different set of hardware. And they know that maybe there will be a slightly different performance, but the computation will run in an almost identical way. And we are nowhere close to being able to support this kind of fungibility. And a third part of it is basically multi-tenancy. As I mentioned, like one of the key advantages of the single controller model from the first wave was the fact that you had these workers which could be shared by multiple different clients. And we kind of sacrificed that in favor of performance when we moved to the second wave. And given the focus on cost efficiency, we are kind of, again, at the cusp where we basically need to have this multi-tenant systems. And one of the key examples that I usually like to show is this pipeline parallel schedule, which basically has, if you see the bottom, the x-axis is time, the y-axis is, let's say, 4 sets of devices, and each of the blocks is computation. And if you use pipeline parallelism, you are inherently left with this bubbles of computation, bubbles which underutilized a large chunk of these devices. But if you could support multi-tenancy, it's very easy for you to just pack this bubble with computation from a different client. And therefore, the accelerator utilization would go to near 100%, while none of the users would actually have perceived any of these, any added latency. Yeah, I'm just trying to think if I want to talk about pathways or skip it, but maybe I'll just briefly cover pathways as well. So I was fortunate enough to work on the system called Pathways, which tried to solve some of these challenges that I just outlined. So Pathways is obviously a system for efficient and distributed ML computation, geared specifically towards this third wave patterns of computation, but it is also intended to drive research into how to increase the efficiency of shared ML infrastructure and enable researchers to move beyond the fairly narrow current default of ML training as a single SPMD computation. So Pathways is basically designed as a cluster-wide runtime for a large pool of shared accelerator resources. And one of the requirements of the design is that the user's Python code runs in a process that is detached from the processes that is hosting the accelerators. So this is, again, like separate from the second wave systems. And the reason why we need this requirement is that it allows us to virtualize the accelerator resources so that we can do things like transparent migration from one set of accelerators to another without interrupting the user's running code. So very quickly, I'm going to cover like the Pathways programming model. If you're familiar with JAX, then the Pathways programming model is actually fairly similar to JAX. You can, the only difference is you can construct, we have this annotation called Pathways program, which allows you to specify how computations can be strung together. So the 3 computations A, B, and C here are basically each potentially running on different sets of devices. So each of them in this case are, let's say, running on two sets of devices. And then the graph here defines how the data flows between these computations. So the 3 computations themselves are SPMD computations, but the overall program is actually not SPMD. So it's basically a graph of SPMD computations. So you basically start with this program, which is specified in it's basically just a front end, right? You could substitute with it with any programming language of your choice, which emits the sharded data flow program. And then this sharded data flow program is executed on a shared set of accelerators that are managed by the Pathways runtime. So in this case, it has, for simplicity, just three different sets of accelerators that are shown here. And the Pathways controller places these computations on the right set of devices, and it takes care of any communication or data transfer that needs to happen between these computations. So for instance, A is going to communicate with B. I guess A is also going to feed into C, and then C is going to feed back to A. So all of those things are taken care of by Pathways. One of the key things to note here is that there is sharing of accelerators. So for instance, like here, B and C are actually placed on an overlapping set of accelerators. So in that sense, it's actually multi-tenant because you could pack multiple computations onto the same set of accelerators. I'm not going to go into the scheduling because it's, so describing pathways in and itself is going to take a full hour. But one of the benefits that I mentioned is fine-grained time multiplexing. And here I have basically two sets of timelines. The first one shows each color is basically a different, a computation from a different client. And the rows are basically devices. So in this case, I'm showing the computation running on 6 devices. But usually these clusters would be, let's say 4096 or so chips. So you would be running this computation sharded across 4096 chips. So what the first graph shows is pathways can very easily time multiplex between for very small computations of the orders of few milliseconds. And you can get really high accelerator utilization that way. The second is because you have this control over time multiplexing, because you have this single controller design, you can also you can also do a proportional sharing of the accelerator. In this case, you are basically devoting the accelerator time much more to this pink computation as opposed to the blue or the orange computation. For instance, you may have like some high priority computation that you want to run at a much faster rate, and therefore you give it a larger slice of the accelerator, and then you have other computations that you give basically smaller slices. So does that mean that we actually ended up solving all of the problems that I just outlined? No, it's not even close. It was basically a proof of concept system, and there's a lot of these problems that still need to be solved. For instance, we did not, we are far away from fungibility. We did not address fault tolerance. And even though our programming model did not support vectorized data-dependent control flow. So things like the mixture of experts were still not very easy to express, or they were easy to express, but they were not easy to execute on pathways. So a lot more outstanding problems. Pathways was just one of the systems. I expect there to be other systems that will come up in the next few years that tackle some of these problems. So again, like this may be a good checkpoint for me to take any questions before I switch to more the inference side of things.
I guess there's no questions. We can continue, and then we can take questions.
Yeah, I'll try to like breeze through it and maybe like leave 5 minutes at the end. So great. So when it comes to inference, basically often many people who are not necessarily actually closely tied to providing inference, especially inference as a service, they don't necessarily realize the the complexity of the problem itself. We are basically trying to optimize in a very complex multidimensional search space, right? We have 5 different metrics in this case that we optimize for. There are probably a few more, but let's talk about these 5. One is just the latency, like how long does it take to process an inference request? And we want that to be small because that's what the user is going to perceive. The throughput, which is basically how many requests we process in a unit time. These are latency and throughput are kind of fairly standard. There's availability, which is how much redundancy you need to have and your ability to scale out to handle any spikes in traffic. The cost, you can make things highly redundant and available, but it is obviously going to cost you. So, and for accelerators, it's usually dominated by the accelerator time. And finally, the quality itself. Often for these models, you can actually tune various parameters of the model itself to sacrifice quality to gain latency. For instance, one brute force thing is you can just reduce, you can train a smaller model, right? Instead of, let's say, a 100 billion parameter model, you can serve a 10 billion parameter model, and then you would cut latency by a big factor, but you would obviously sacrifice quality. A second kind of knob that you have is just the precision that you use for the computations. So instead of doing full float precision, maybe you can do a half precision or FP8 precision, which just uses like 8 bits, and then or int8 precision. And all of those are ways of basically approximating the actual computation that you want to run, and therefore they would sacrifice quality, but you would get improvements in latency. So we at Cohere obviously have developed an inference framework that applies a bunch of these optimizations that are inference specific, including doing like low rank weight tree parameterization, quantization, using techniques like flash attention. And there's the link to a blog post on Cohere's website that actually discusses some of these optimizations. There's also an interesting paper that came out, I think sometime last year, which specifically talked about efficiently scaling transformer inference. And there were two key ideas for optimizing LLM inference. The first is basically an analytical framework to search for the optimal partitioning strategy. As I mentioned, the search space is fairly complex. So if you have an analytical framework, you can explore many more data points relatively fast and get to find some optimal configurations, including like the specific tensor layouts, the resharding that you need to do, and so on. And the second is something called using multi-query attention instead of multi-head attention. In the interest of time, I'm going to just skip that, but I would recommend, if you're interested in this space, definitely check out this paper. It's a nice read. The second thing to note is often what we have seen is there are these standard serving frameworks, whether it's TensorFlow serving or Triton inference servers, that are good at serving generic types of models. But if you want to eke out the performance, last bit of performance, then you kind of need to develop customized serving solutions. In our case, we want to develop customized serving solutions that are specific to handling tasks that our API needs to handle, which are mostly text-based. This is an OSDI paper that came out last year, which basically talked about how to develop optimized systems specifically for serving transformer-based generative models. And through some of the techniques that they mentioned, you could actually get a 40x throughput improvement at the same level of latency, which is obviously like dramatic. And there are two key ideas. Again, in the interest of time, I'm not going to go into the details of what the two ideas are, but I would encourage you to check out this paper again. The third is we basically are increasingly moving towards a world where the foundations model do not necessarily give you the last bit of performance needed for a specific task. So you would want to start with the foundation model, but fine-tune them for your specific tasks so that they get really good at the domain that you want to target it for. And if you want to do that, then we need a cost-effective solutions to serve a large number of these fine-tunes for the same underlying foundation model. So the naive approach obviously is, if we have 1,000 customers, each of them have their own fine-tunes, we assign a single accelerator for each of them. But that's just almost cost prohibitive. A better approach is potentially you use the host memory as swap space, and you swap in some of the weights for each of the customer whenever they are using it, and then you swap them out. And that might work. But it will have the added latency because you would be swapping stuff in and out of the high bandwidth memory of the GPUs. An even better approach is you only fine-tune a small fragment of the base set of weights and you stream them from the host. So the base set of weights of the foundation models are always resident on your accelerator memory, and you're keeping the small amount of fine-tuned weights in the host memory. And then whenever you get a request, you stream them back to the GPU memory, and then you run the computation. And that, again, is potentially a better approach. And lastly, there's the best approach, and one that we are currently pursuing, is use some form of an adapter network that allows you to basically serve n number of fine tunes using the same hardware without worrying about swapping weights in and out. And potentially this also enables things like transfer learning, so that you don't necessarily, you can update some of the shared set of weights in addition to adapting to specific customers. Right, I think that's pretty much all I had to say. So to summarize, I basically gave you a historical perspective of how ML systems, like how ML hardware, the models themselves, and the systems that are built on top of this hardware have evolved over the past decade or so, what kind of challenges we still face, and what the next generation of systems should look like in order to be able to handle these new types of workloads. Presented some preliminary work that has happened in the space, but there's still lots of interesting and challenging technical problems to solve. So that's it. Thank you.